Hello, everyone, and thank you for joining us today for the presentation on defining sparkle measurement standard for quality controlled anti-glare displays. I really appreciate you taking the time to be here. My name is Matt Schultz, and I'm the automotive business leader here at Radiant Vision Systems. I have over 10 years experience working in the automotive industry, specifically working with metrology equipment, specializing in looking at interior, exterior, automotive lighting and display technologies. Through my time in the industry, I've had the opportunity to work with all the major tier groups through to the OEMs on various types of applications, from R&D to QA to, of course, end-of-line applications. And throughout my time, I've had the opportunity to witness different types of technologies implemented into the automotive vehicles. And today I want to talk about one that's becoming more prominent, which of course is the addition of anti-glare films and coatings. Before we begin, a quick reminder that I will host a live Q&A after this presentation. The presentation should last approximately 30 minutes, and you're welcome to ask any questions at any time. I will queue and answer any questions that have been submitted at the end. To ask a question, please use the questions window in the GoToWebinar interface found on the right side of your screen. You really can just type your question, please click send. So a little bit about Radiant Vision Systems. So here at Radiant, we manufacture 2D metrology equipment. We specialize in imaging photometers and imaging colorimeters to characterize light and color applications. We work within the automotive industry, consumer electronics, medical, aerospace, solid state lighting. We've been around for 25 years, and we have the privilege of being part of the Konica Minolta group of companies. Working with Konica Minolta has allowed us to expand our global approach to really provide a worldwide solution to our customers, regardless of location. Today's agenda. So I'm going to go through anti-glare displays as a starting point, the background and the applications, the effects sparkle has on displays. Then I'll jump into basically a sparkle measurement study that we conducted. I'll talk about what we did to define acceptable tolerances, the scope of the overall study, of course, the experimental setup of the study, and then the general results of our investigation. So let's talk a bit about the background and applications of anti-glare displays and the effect of anti-glare properties on visual display quality. Displays exposed to sunlight are hard to read due to glare. For mobile devices and display orientation and subsequently being able to change and minimize the amount of glare, this truly isn't an issue. But when we look at, let's say, automotive-related displays, where these have a fixed orientation in a center stack or instrument cluster perspective, anti-glare and anti-reflective treatments become important for this display technology. Here we can see how the reflection on display in a car dashboard can severely impede the visibility of display information. The operator may shift their position to view the display from a different viewing angle, but ultimately the reflections can't be changed as the vehicle moves, making this an arduous task for the driver, whose focus should be on driving the car and not paying attention to display technology. Anti-glare films and textures are applied to displays to reduce these specular, mirror-like reflections from the display glass or plastic. Anti-glare coatings are actually a micropattern or roughened surface of a substrate or immediately below the substrate's outer layer that use diffusion mechanisms to break up the reflected light off the surface. Diffusion works by reducing the coherence of the reflected image, making these unwanted images unfocused to the eye, thereby reducing their interference with the viewing of the intended image contained in the display, like we see on the left side of the example here. Age treatment can, however, negatively impact the visual appearance or clarity of the display. This image shows a very close-up perspective of what happens when display pixels are viewed through agey layers. At a distance, this refraction of light from each display pixel can result in a hazy appearance that can also impact visibility. Operators may spend critical seconds trying to decipher information from an agey display that appears low clarity due to agey properties. Overall, user perception of the display's quality or vehicle quality may be impacted due to the influence of agey coating on the display. With the increasingly critical impact of displays on operation and experience inside the vehicle, the effects of anti-glare displays need to be verified. We want to have a verifiable method to check the impact of agey properties on a display. This method relies on the measurements by an automated visual inspection system. In the measured images captured by an image-based display test system, as in this example, the application of the AG layer introduces properties including sparkle, haze, and diffusion, or glare. These are some of the most common visual effects that we see in AG layers that can be measured with various technologies. AG microstructures act as small lenses. The light from the subpixels is refracted by the AG microstructure, producing sparkle dots, which is kind of like visible noise. The principal drawback to using diffusive mechanisms to address external reflection has been that they sacrifice the clarity and the resolution of the intended image. Mechanically or chemically textured surfaces or anti-glare coatings using suspended particles reduce the glare, but often at a significant trade-off of image resolution and readability. While economical to apply, the trade-off in image resolution and clarity represented by these anti-glare treatments often makes them an inferior solution to a manufacturer's viewing requirements. Sparkle occurs when the AG surface structure competes with the pixel geometry of the display. As display pixels near the size of the facets in the AG film structure, light emitted from each display pixel is refracted by AG surface variations that cross the pixel area, causing interference and scatter. It really is a delicate balance, though. We want to optimize AG layers to look at the maximized diffusion of sunlight and then look to minimize the impact of sparkle on the image quality. Quantifying these effects can help us compare the severity as well as reduce anti-glare coatings and texture level variability from display to display. We need to use a quantifiable measurement method, then to first achieve the sparkle value, and then of course correlate this to human perception studies to understand what level is acceptable to the human observer and what falls below that level of acceptability. With respect to sparkle, the testing methods that measure the standard deviation of peak luminance across the display based on a measurement image of the display with an AG layer applied. A photometric imaging system captures an image of the AG display for analysis. Then, connected software processes the image and evaluates the luminance values across the display, or across the acquired image in this situation. A typical sparkle analysis first divides an analysis region into subregions. For each analysis subregion, the sparkle analysis measures pixel-level luminance and calculates the standard deviation for the subregion. This standard deviation is the sparkle value for that specific subregion. After a standard deviation calculation is made for all subregions, an average of all the subregion sparkle values is calculated to output the final sparkle percentage. This percentage is the measured sparkle for the display, which is also known as the sparkle variation. We want to apply an objective measurement method to qualify the effect of sparkle seen in AG displays. This way, manufacturers can set tolerances for how much sparkle is allowed within their displays. We can ensure qualified displays meet visual quality tolerances to an objective numerical value. Ideally, our sparkle measurement method will enable an automated inspection device to provide repeatable characterization of sparkle, which agrees with our human visual perception of what a high-quality display really should look like. So the questions that we want to sort of look at are, how do we quantify what an acceptable amount of sparkle is? How do we quantify this value consistently? What are the measurement systems that we could use? And how do we set up a consistent measurement process? And how, of course, do we obtain repeatable sparkle values that always correlate with what we deem is acceptable? In other words, how do we effectively automate the qualification process for sparkle variation analysis? From our last Ring Vision Systems headquarters, we recently conducted a sparkle measurement study to evaluate the effectiveness of various system specifications and measurement parameters to really help us define a standard method. I'd like to walk through that study and our results. We had the great privilege of working with several different automotive OEMs to define the measurement process for sparkle that really correlates with human visual perception. An initial study that was performed in cooperation with Honda using a selection of displays from their suppliers for benchmark testing allowed us to look at 10 different supplier displays, which each had a different level of AG coating or film supplied to them. We took 10 different human inspectors, and then the 10 human inspectors looked at each display and we ranked them from best to worst. Once all the displays were ranked, Radiant used a prometric imaging photometer to measure each display using our sparkle analysis in our software. We then ranked each display based on the percentage of sparkle variation measured by the automated system and compared these results against the human inspector's perception. Here we see the results of this study. So looking at the illustration, we can see that nearly there's a one-to-one correlation between the human observer's display rankings and the quantitative measurements provided by Radiant's prometric automated measurement systems. The study was performed several times by engineers at Honda and Radiant's representatives to show the repeatable correlation of human evaluation of display quality as affected by perceived sparkle to the quantifiable sparkle percentage as measured by the Radiant system. This method has proven effective in several customer applications. However, there are a few areas that have provided opportunities for refinement. At Radiant, our goal is to test out potential variables to define a standard method that can be easily applied by any manufacturer in any measurement condition, using our equipment to get repeatable sparkle measurement results. Our method has two initial assumptions. An evaluation by human observer must be carried out to determine a golden sample of a display that exhibits acceptable levels of sparkle. This sets our tolerance, which we need to quantify for repeatable, accurate measurements through the automated process. A standard unit of measure is assumed to quantify the sparkle effect as a value, which is a percentage for the standard deviation across the display, as we previously described. In order to refine this method as a true standard that can be applied universally for repeatable results, we need to test the following: our various test systems and specifications, the parameters of the measurement setup, and of course, the effect of various software or image processing functions. Ultimately, we want to define a standard measurement method that provides repeatable results for sparkle analysis with the Radiant Vision Systems equipment. And from our experience and our success in the market, we believe that we can refine the sparkle measurement setup so that manufacturers really can define an absolute sparkle value as a standard tolerance and qualify this metric for their displays. This is based on using a consistent measurement setup, specific parameters, and software functions that have been tested in this study. In our test, we employed the prometric imaging systems ranging in various resolutions. Each one of them was paired with a 50mm lens. These devices primarily use scientific image sensors with a calibrated photometric or colorimetric filters, built-in neutral density filter wheels, and electronically controlled lenses. The measurement output from the software and the device in its most basic form is pixel-level detail for luminance and chromaticity. All additional analyses, including sparkle variation and standard deviation, are derived from these measurements. The software used was Radiant's TrueTest automotive display platform, which specializes in the feature for sparkle analysis that measures the standard deviation to yield a final percentage value. We measured 3 automotive center stack displays with varying levels of sparkle as defined by human observers. In the measurement results in the coming slides, you will see we've labeled these displays Display A, Display B, and Display C. Through a ranking from human observers, Display A was determined to have the least amount of sparkle, and Display C has the most observed sparkle. Here's an example of a test bench that Radiant Vision Systems has utilized for sparkle measurements that allow for automated sparkle characterization. Under given test conditions that we will discuss throughout the presentation, a similar system can be built where displays can easily be evaluated for certain quality parameters related to sparkle. To eliminate variables in our study, our measurement setup was strictly controlled. First, alignment of the imaging system to the display is critical. We know that off-axis alignment has a direct effect on the data and the sparkle variation due to the luminance dependency on angle. Here, we utilize a measurement setup that was defined within the German Flat Panel Display Forum, also known as the DFF. This setup is most commonly used with the black mirror gradient or BMG alignment image and analysis process. Software can be used to ensure accurate alignment and orientation of the display. Using Radiant's TrueTest automotive display software, we use a software alignment window and a test image. Here you'll see the grill pattern in the test image is used for the camera alignment and is the same as seen in other applications that I mentioned for black mirror, which is in regards to the DFF standard. This test image displays 5 dots that can be used as reference points in the software to perform a calculation of the offset of alignment and rotation between the camera and the physical display. This just guarantees that the setup is properly aligned to a reasonable offset of tolerances. The information you can see here in the slide really is showing us the following 2 things: axial rotation of the area and the angle and position of the DUT to the measurement device. Once alignment is complete, we want to push out a green pattern to the display. We select green because this image, based on human spectral sensitivity to green light, is the most accurate to identify sparkle variation. We know that we perceive these colors as more intense or more powerful, so the visual properties of something like sparkle effect should be more extreme on a green image. We match this human spectral sensitivity in our cameras, which is common when we're looking at our tri-stimulus colorimeters, which of course use CIE matched color filters. Other test image colors could be projected depending on the measurement process and goals you're looking to achieve. The same process would apply when pushing different colors though to the display. For repeatable measurements, a specific focus should be defined and used for each subsequent measurement. We will discuss focus later as a variable test in this study. Working distance is also an important parameter for setup. We tested this variable as part of our sparkle measurement study. Each distance was tested against several displays for statistical evaluation. For repeatable measurements, a working distance should be defined and used for each subsequent measurement. We will discuss this measurement parameter later as a variable, again, tested in this study. And before we get to the measurement, the final element of our setup process includes an active display registration step. When looking to register a display, it's critical to ensure that you identify only the emitting area of the display. For this, we took advantage of Radiant's automatic register active display area function, which we call RADA. In cases where the optimal orientation and position does not account for the discrepancies in the display's rotation or causes negative space around the display, RADA is able to report the corner pixel locations in the display and automatically rotate and crop images for precise measurement of the intended display area at normalized X and Y positions. Competitive systems that don't offer a RADA-based system may report sparkle with inconsistent results, preventing repeatability. While the measurement system is set up, we looked at the following variables as part of our study. So we wanted to understand system resolution, MOIRÉ, system focus, which of course is modulation depth, the effects of gradients, the size of the analysis region, the detector size used for analysis, and then the various working distances and how those have an effect on our results. So let's take a look at each of these variables that we tested and the results for each one. The first variable we tested was the system's resolution's impact on sparkles from a measurement repeatability. The impact of resolution was tested by measuring the same display at a set working distance and focus distance with different image systems resolutions. The resolutions we utilized were between 2 and 29 megapixels, which you can actually see shown on the column on the far left side. In this table, we're showing the results of testing a single device in our test. In this situation, we're looking at display C. We can see that from the output sparkle measurements in the column on the right, in the red, that there is very little measured variation between resolutions, really less than 0.1%. These results indicate that if measurement setup is consistent and the same sensor technology is applied, resolution of the sensor has no effect on the measured sparkle value. The next variable we tested in our study was the effect of MOIRÉ on sparkle measurement repeatability. MOIRÉ is the aliasing effect that results when a sensor-based system captures an image of a pixel-based display. The pixel array in a sensor can compete with the pixel array in the display, causing MOIRÉ to appear in the images. This may require an image processing method to remove the effect from the measurement images, so it does not impact the overall measurement, the measurement results. Radiant has a proprietary MOIRÉ removal method that eliminates this aliasing effect in images without losing detail in the image itself, which may be as small as a display pixel. Here we have some images of the results of that specific method. Another method of eliminating MOIRÉ's impact on measurements is by defocusing. This is a standard method found within the DFF related back to the Black-Murrah gradient analysis. Defocusing can remove the appearance of moiré in measurement images, but it is important to note that pixel-level details in the image cannot be preserved if we follow this defocus routine. This is just something to consider if you're looking to apply additional analyses at the display level. In our study, the impact of moiré on sparkle measurement was tested by measuring each display and comparing results with and without the Radiant Vision System's moiré removal algorithm. The impact of moiré removal was also tested as a function of the detector size used to measure the standard deviation. More information will be provided about the impact of detector size on the analyses as a key measurement parameter later on in this presentation. But in this case, using different detector sizes is just to give us a way to illustrate the impact of moiré and how it affected the overall removal process. Let's take a look at the following results. In these plots, our three devices under test are plotted as blue, orange, and gray lines. So again, A, B, and C, and the abbreviation SD refers to the standard deviation. First, looking at the two bottom graphs, we can see how the sparkle percentage deviates with or without moiré removal across the same range of detector sizes. As we discussed earlier, display A was determined to have the least amount of sparkle, and display C was determined to have the most. However, when looking at the comparison of the bottom two plots, we can see that this order changes before and after moiré removal is applied. Looking at the bottom left plot before moiré removal, display A is still trending as the lowest amount of sparkle, but display B is measured as having a more severe sparkle than display C, which we know from our human perception study not to be true. Once we apply moiré removal in the bottom right plot, we measure the display sparkle in an order that matches human visual perception, with display A on the bottom having the least amount of sparkle and display C consistently having the most measured sparkle at the top. What we can conclude is that we need to apply moiré removal in our measurement conditions to ensure correlation to human visual perception. As we can see, moiré affects measurements, so we either need to remove moiré using an image processing technique as illustrated by Radiant's moiré removal methods, or look to defocus, which is another common method. This brings us to a variable of system focus and how that plays a role in our sparkle measurement repeatability. The impact of system focus was tested by measuring three automotive displays again, the same A, B, and C that I've already talked about, at a set working distance using different focus distances. A standard working distance of 1 meter was chosen for this study to correspond to working distances in current automotive measurement methods to comply with developments happening across various standards in the SAE, DFF, and ICDM. Looking at this graph, we can see that the measured sparkle value changes with focus distance settings. As the display becomes more or less in focus, the sparkle value increases or decreases. However, the correlation between the displays based on human perception remains relatively constant, meaning that the display the observer perceives as the worst continues to look poor compared to those that were ranked in higher quality, and that the value between these displays remains constant. It is just that the absolute sparkle value here that is ultimately affected by focus. What this means is that we can still see repeatable results compared to human perception if we can find a way to repeatably change the focus level to a known and defined value. We just need to set a standard focus. So then the question is, how should we define this defocus process? Can we go through a process in understanding what the effects of moiré are and how to drive our standard forward here? Looking at the graph here on the left, you can see the percentage changes measured as sparkle as a function of focus distance. This shows us that the measurements in sharp focus around 0.97 meters of focus distance, moiré has a significant effect. This is similar to what we saw in our moiré testing earlier. It also shows us that certain focus levels, the moiré is naturally removed from the measurement, and therefore the system should be defocused to a level in line with these focus distances. As an additional test for our study of the effect of system focus on sparkle measurements, we calculated the modulation depth percentage that optimally defocused the measurement to reduce moiré and give us a repeatable sparkle measurement value. To test what was acceptable as a value for defocus, we started by measuring display B at our set working distance of 1 meter, and then we decreased the focus distance from the optimal focus. Sparkle measurements were taken until there was no difference between the results with or without the MOIRÉ removal processes. This means our focus setting at this distance are as adequate as MOIRÉ removal processes. The focus distance where these results converge is found to be a distance of approximately 0.92 to 0.93 meters. Using the Radiant Vision Systems BMG defocus analysis that follows the DFF Blackmura standard in determining an acceptable level of focus, the modulation depth at this focus distance was found to be 67.5%. Using the same analysis, a modulation depth of 67.5% with a tolerance of 2% was set as a target defocus level. When the appropriate focus distance was found, sparkle was measured 3 times. This routine of defocus and 3 sparkle measurements was performed 3 additional times. The results are shown in the table on the right. You will see that there is a very small variance between the measured sparkle values. This tells us that using this defocus routine can remove the influence of MOIRÉ in the measurement, and that 67.5% modulation depth is acceptable from a standard value to defocus at 1 meter from a working distance perspective to ensure repeatable sparkle characterization. The next variable we tested was the gradient. Like MOIRÉ, gradient is a common issue in display measurement images, which can cause unreliability in sparkle measurement data. It can occur from variations in the system's optics and can also be a characteristic of the display, like changes in the brightness or the uniformity across the display. Because standard deviation is used to calculate the sparkle in AG displays, broad gradient changes across the display must be normalized to achieve accurate measurements. Where no gradient is present, the standard deviation is calculated accurately across the display using min and max luminance values. Where a gradient is present, though, across the display, standard deviation is calculated inaccurately because the min and max values characterized are by the gradient rather than the luminance variation. This image shows how large our standard deviation may be for an area that has a broad gradient shift. Here's an actual measurement example. We have 2 measurement images of the same display covering the same region of interest. Radiant employs image processing using a gradient filter to remove gradient effects from the display. The image on the left shows the display before the gradient filter is applied. We see broad changes in luminance that are observable from dark at the bottom to light at the top. And then the image on the right is after a gradient filter is applied. When we measure each of these images for sparkle, we can see by the result that the gradient impacts the value. Basically, gradient is being incorrectly measured as sparkle in the image on the left when it is actually a completely separate visual effect in the overall image. To find a standard for our study, the effect of gradient on sparkle measurements was tested by applying different gradient filter sizes in Radiant software to each display, A, B, and C. The graph shows that the measured sparkle does not change with a gradient filter size of higher than 5. Any filter size below this will have a strong and dramatic effect on our results. To normalize the potential effects of the gradients across the display, which may cause errors in standard deviation measurements, a gradient should be applied during the measurement process. This filter is available in Radiant's TrueTest software packages by default. The next variable we tested in our study was the size of the overall analysis region. The impact of the analysis region size was tested by comparing measured sparkle from the center of the display, where a conventional sparkle measurement is typically performed, to the edges of the display. The regions are compared as a grid. What we found is that the gradient filter is applied, then the sparkle values do not change significantly whether the measurement is at the center of that or at the edge. With this, an entire display can effectively be analyzed for sparkle. A manufacturer may also choose to subframe the display region to a smaller analysis region while achieving consistent results. This may be helpful when fixturing between the display and the camera may vary slightly in the XY position. The next variable test that we looked at was the impact of the detector size on repeatability for sparkle measurements. We should define detector size a bit here though. If we have an analysis region like this on the right that we defined for the display, what we want to do is divide up the display into these squares to get the standard deviation of each area and average them to find the overall sparkle value. Virtual detectors are then placed within each area by the analysis software. These are just a representative example of the detectors in this image. There could be more or fewer, and they could be of various sizes. Each detector requires a luminance value, which is used to calculate the overall standard deviation of this one area of the analysis region. This is done for each area of the analysis region, and then ultimately the standard deviation values of each region are averaged to give us our sparkle value, which is a single percentage value. What we want to know is, does the detector size impact the sparkle value that we get after all the calculations have been made? The impact of the detector size was tested in our study by measuring sparkle on each display, again A, B, C, with varying detector sizes. In these tests, MOIRÉ removal was already applied. We saw the plot on the left here in our MOIRÉ removal testing results. Looking at the detector size in particular, what we see is that as smaller detector sizes are used, the standard deviation increases significantly due to pixel-to-pixel variation in the measurement image. Say, for instance, our detector size is very small. We have few display pixel values to calculate the overall detector value. If there is a dead pixel in our detector area or a very bright pixel, the detector value could vary dramatically from the value of the other detectors. A larger detector size reduces the influence of these small pixel level variations. At a larger detector sizes, the standard deviation is reduced so much that the difference between the three displays is almost negligible. Display B at detector size 2 millimeters is considered to be considered much worse than C. What we want to do is choose a detector size that is not so small that any severe pixel level variation in the display may be impacted and the severity of the sparkle measurement may be compromised. We also want a detector size that is not so large that it averages out so much of the pixel level variation that our sparkle values converge between our displays. For instance, in the plot to the right, we are looking at the effect of the detector size on the correlation of our displays. Measurements are normalized to the best display, which in this case is display A at the bottom with the blue line. At a small detector size, the displays diverge dramatically in their measured sparkle value. When the detector size reaches 2 millimeters, this causes sparkle values between displays B and C to converge. However, we know from our perception study that display C is worse than display B. So a detector size of 2 millimeters, we're averaging out far too many pixels from a variation perspective, and the sparkle value is being inaccurately measured. Both of these extremes give us less reliable output. Our study shows that a detector size between approximately 0.3 millimeters and 1 millimeter truly is ideal. To determine the impact of working distance, the sparkle of a single display was analyzed by varying the distance between the measured display and the imaging system sensor plane. The detector size was the same across all working distances, and the system was focused at each working distance. The only variable measured in this case was the working distance itself. As we can see in the graph, the measured sparkle varies with the working distance, which is expected as the ratio of sensor pixels to display pixels varies as the imaging system is positioned closer or farther away from the display. This means that a standard working distance really must be defined. To align with other automotive measurement standards, a 1 meter working distance is recommended for sparkle measurements, with other standard parameters proposed throughout the study as a factor of this working distance. The conclusion of our study was that some variables require standardization and some do not. Of the system settings and parameters that do require standardization, MOIRÉ definitely influences the measurement results. Determining an effective way to remove MOIRÉ through defocus routines or MOIRÉ removal tools is essential to measurement accuracy for your test. System focus is also a parameter to truly consider. Based on our study, the correlation to human perception does not change with focus, but absolute sparkle results do vary based on focus, making measured values diverge from human perception rankings. Therefore, we need to identify a specific focus level based on modulation depth to obtain repeatable results that accurately correlate with our perception. Gradient in the display or the measurement image definitely has effect on repeatability. Therefore, we need to look at applying a gradient filter that removes these effects of any gradients found within the acquired test image. Detector size also matters. Small detector sizes pick up small display variations, such as pixel level luminance differences that give sparkle its visual quality, where large detectors average out the effects of these variations. The sweet spot really lies between 0.3 millimeters and 1 millimeter. On the other hand, though, resolution was deemed to have a negligible effect on the sparkle measurement. If you're just evaluating sparkle, resolution of the imaging system really is not critical. However, if you wish to inspect the display for other aspects like particle defects, a pixel, or pixel-related defects, increased resolution does become important. Through sequence-based analyses, you can quantify both of these. However, to reiterate, for the base level sparkle analysis, resolution was deemed not to play a critical role in the accuracy or repeatability of the measurements. And then finally, the analysis region size. Evaluation of any size region of the display is possible. When gradient filter is applied to remove gradients from the measurement images, the results from the center of the display to the edges will not play a factor in the sparkle variation percentage measured. Any area of the display used as an analysis region will provide equivalent results for overall sparkle of display. The region could be the entire active display area or it could be subframed down. It really depends on the end user's application. With all of these results taken into account, here's Radiant's proposed sparkle measurement method. This method ensures repeatable sparkle values are obtained across measurement scenarios, devices, and systems. By achieving repeatable values, this method enables standard tolerance settings for automated display qualification across manufacturers' processes. The standard method really includes the following: an imaging system like the Prometric imaging colorimeters or photometers, utilizing any of the resolutions available, the software found within the TrueTest automotive display suite, looking at the sparkle analysis, having an alignment tool that uses the BMG alignment image, projecting a green test image, looking at your analysis region, which we've identified could be of any size, looking at image processing techniques, so something like RADA being applied, MOIRÉ removal or a defocus routine, and of course, a gradient filter being applied. Modulation depth is 67.5% with plus or minus 2% tolerance is acceptable, and detector size has been ideal or determined to be ideal around 0.3 to 1 millimeters. And again, if we're working within the automotive industry, we see that the specifications right now are discussing working distances of around 1 meter. To summarize, anti-glare layers improve display visibility in reflective light, but they do introduce sparkle, which can affect the perceived quality of the display. Lack of a repeatable measurement method for sparkle has been a barrier to defining a standard quality for control processes. A method employing the Radiant Prometric imaging system, the TrueTest software, and the defined measurement parameters has been proven at automotive OEM facilities for repeatability with direct correlation to human perception. Using this method, OEMs and manufacturers of displays can set precise tolerances for sparkle and define standards for quality control. That wraps up my presentation. At this point, I'd like to move into the Q&A portion of our webinar. If you have to leave at this point, I really do thank you for your time. Feel free to reach out to us if you have any questions at the address found here on the slide. For those who are staying, remember you can send in questions for the Q&A by using the GoToWebinar control panel. Type your questions in the questions window and send it to us, and we'll try to get to as many questions as we possibly can.
So yeah, we do have some questions coming in. First question I got here, do we need to run a user study at each facility to determine a sparkle tolerance for each location, or is the sparkle tolerance we set universal across all locations?
Yeah, so that's a really great question. And if you're following the same procedure, so if you're using, similar resolution cameras, but following the same working distance, the same gradient process, the same detector size, you should be able to set up measurement parameters that are deemed acceptable at one facility and then can be implemented at others. Really, repeatability of the measurement process is the critical aspect here for determining accurate results from site to site.
Great. Another question here, should we use the same camera for all sparkle measurements, or can different cameras be used?
Yeah, so I guess you could answer that in two ways. So as I talked about, resolution is not critical, right? So Radiant offers several different imaging platforms, from imaging colorimeters, which we call the I series, to imaging photometers, which are the Y series. Since we're only using the V lambda filter for this measurement, and as I said in the presentation, resolution is not critical, you could use different resolution systems. You could use an I8, which is an 8 megapixel system to take a measurement, and you could also use a Y16, which is a 16 megapixel system, both with different design processes, but again, both built by Radiant. And you could acquire the measurements and achieve basically the same levels of results and repeatability across the two of them. Now, if you look at systems outside of the Radiant product line, in theory, there could be some solutions that work. And as we know, the ICDM and SAE are looking at creating a process that is standardized. And we believe, working with different people within those organizations, that our process really is headed in the right direction. And being part of those studies allows us to have a strong influence in understanding the requirements. So again, sort of long-winded answer, but it is possible with the existing radiant technologies to use different resolutions, different camera technologies, and then outside of that, based on standardization, it could also be potentially possible.
All right, thanks, Matt. There's a question that just came in about, was any work done on obtaining sparkle values at viewing angles other than normal to the display?
Yeah, so viewing angle definitely has a strong characteristic for what we're looking to observe. In this study, I didn't talk about that, but that is something that we have looked at. Obviously, with the angular dependency from a luminance perspective of display technologies, we do see an offset result, which is why I mentioned earlier on, alignment to the display is critical if you're looking for repeatability. But of course, our technology does give you the opportunity to look at off-angular perspectives, maybe something like a center stack display from a driver to a front passenger position, and seeing how that angular dependency plays on the different types of coatings or films that are applied to these displays. So that could be done. Unfortunately, with this specific study, I didn't share any of that data, but we do actually have a good amount of that acquired over the last several months, that if someone really wanted to, I could share with them afterwards.
Great, thanks, Matt. Another question just came in. Can the software report out the sparkle percentage as a part of IQC or OQC for a display supplier, for instance?
Yeah, most definitely. So, we work with film and coating manufacturers who, a tier 3 who might manufacture specific films that are anti-glare and property, or we might work with a glass manufacturer who's applying the coating. But of course, those components end up on a physical display. And in this situation, maybe an automotive center stack or an automotive instrument cluster. So we actually can set incoming quality inspections and outgoing inspections to ensure that, the combination of these technologies meets an appropriate quality perspective or standard process that maybe from an automotive perspective, an OEM might have set. And this can be pushed from, OEM verifications down through maybe the tier 1 who might be creating the final product.
Okay, great. Question here about working distance, if you can measure from a working distance other than 1 meter, as we showed in the study.
Yeah, of course. So again, repeatability is really critical for your measurements, but we use 1 meter because we were focusing really on the automotive industry, and we're seeing that the standards are moving in that direction. But we've done a lot of work previously where we worked at 0.5 meter. And if you were to set up your measurement parameters for yourself or your customers, and you were all following the same routine from a measurement distance perspective, that would be completely acceptable. But of course, you want to really be comparing apples to apples in the measurement scenarios.
Another question, maybe you can handle this one, Matt. What are the minimum and maximum levels of luminance that would be measured in the display?
Oh, yeah, so that is a great question. So we see situations where displays are dropped down for, nighttime settings where they've been dimmed quite significantly to, of course, in a full daylight ambient scenario. Thanks to the dynamic range of our measurement equipment, we really can measure, down around the 1 candela per meter squared range, which is, really, really faint and generally not found to be a display related output level, to, thousands of candelas per meter squared from a luminance channel perspective for each emitting pixel. And then of course, the same process is run where we're looking at the standard deviation within each designated subregion, characterizing those perspectives, looking at the verification of the mean, and then giving a total sparkle variation output for the overall display. Again, the scale of luminance does not have a direct effect on the camera's technology to perceive that value.
Maybe you can describe a little bit about, there's a couple questions about the human perception study that was done initially in these tests. A question on what humans were asked to evaluate and if they were evaluating the displays in a normal orientation, if you have any insight on that.
Yeah, so I was lucky enough to actually be part of the study, right? So when we were working, we've done several human studies, but if I focus on the one that we did with Honda, because that's the one I talked about in this presentation, basically the idea was we had 10 displays set up on a large table, and each inspector was given a chance to run through them. So we designated them 1 through 10, again, 10 different suppliers, and we looked at them as perpendicular as possible. So we would kneel down, look directly at them, and we moved our heads around to see if we could see any sort of deviation in what we deemed the sparkle variation to be. Then we graded them individually, 1 being the best, 10 being the worst, and plotted it out. What we then did was we took the prometric measurement systems and we actually aligned them perpendicular, but we measured them in 2 axes, a horizontal position and a vertical position. The customer and the suppliers were curious if different orientations would have any effect. At the end of the day, we were still perpendicular regardless of the axes, so the measurement results and process was exactly the same. And as I showed in the study, when we started taking the computational information and we started grading it from a percentage perspective with the Radiant software, we saw that the lower percentage values aligned with the human inspectors' observations of what the best quality displays were. So something around 1.7% sparkle variation was deemed as a really high quality display with barely any sparkle or no sparkle that was visible to the human eye. And as we progressed through the other 10 displays, we saw different variations in the overall AG coating qualities or film qualities applied to those displays. And the same thing graphed. As the display got worse, the percentage value went up found within our software platform. So hopefully that provides a little more detail.
Great, thanks, Matt. Good question just came in. Can we use the same camera to inspect other aspects of the display, like the overall brightness, color, contrast, and other things?
Yeah, of course. So that's one of the really nice things about our platform. So we use an electronically controlled lens, which I didn't really touch on too much. But in the presentation, I talk about how MOIRÉ removal is critical. So either you go through using a MOIRÉ removal tool, so you have crisp focus, you remove the MOIRÉ, the aliasing effect, and then you run your sparkle variation. If you do that, you also have the ability to look at characterizing the general uniformity before the gradient is removed. You can look at things like pixel level defects or MOIRÉ blemishes that are found in the display. What's nice is we can acquire one image, run 3 or 4 different sets of analyses, and break them all out individually with their own reporting format. If you decide that you want to go through the defocus routine, you would have to, of course, refocus the camera for a lot of those measurement applications that you just mentioned, Shayna. So uniformity, color, pixel defects, MOIRÉ require a sharper focus.
Great. All right. I think we're going to just get one more question in there, try to be cognizant of everyone's time. So I have one question here about the resolution testing. Can you further explain why resolution would be irrelevant to the measurement like we showed in the study?
Yeah, so here what we're looking at is we set a fixed distance. So when we were looking at the resolutions of our cameras, we have a 2 megapixel, an 8, 16, 29. And each one of those has a different size sensor. So if we position all the cameras at the same working distance with the same lens, essentially when we map out the area of the display, they have the same amount of sensor pixels, because what happens is as the resolution goes up, the sensor size goes up. So we increase our field of view, but the display in section still has the same amount of sensor pixels on the horizontal and vertical channel. A 2 megapixel is going to fill the display with X and Y pixel grades, and if we move to 16 megapixel, we're going to see the same amount of pixels from a sensor perspective found at the exact same working distance over that display, but we're also going to have a much larger field of view, which of course we're going to crop out at the end of the day using something like RADA. So in that situation, resolution is not critical, because when we run our detector size and our location size for each of the subregions, they effectively have the same amount of sensor pixels regardless of the resolution. If we increase or decrease the working distance, that's where resolution starts to add to the play. But again, now we're not following the same measurement geometry and setup, which we've already deemed is critical for evaluating sparkle. So that's fundamentally why resolution isn't important, because the pixel geometry and spacing and resolution over the device under test remains the same based on the same working distance and lensing pairing of the different sensors that we utilize.
Great. Well, thanks, Matt. I think, There are a few questions in the queue, I think, that just deserve a little bit more explanation. So maybe, Matt, you could take those offline, and then we can kind of wrap up here and everyone can have a little bit of an early start to their next meeting. Really appreciate everyone coming to the webinar today. And thank you, Matt, for the presentation and for hosting the Q&A here. If anyone has any further questions or wants more information, you can feel free to visit us online at radiantvisionsystems.com to see our automotive solutions and our display test solutions, or email us at info@radiantvs.com. And anyone we didn't get to, we're going to follow up with you after the webinar. And as a reminder, you will get an email following the broadcast today with the slides and the recording of today's presentation. Again, thank you everyone for coming. Thanks, Matt.
All right, thanks everyone. Have a great day. Appreciate your time. I'll follow up with any outstanding questions. Have a great weekend.
Bye.